everyone. I'm Shivram Venkatraman. I'm a PhD candidate at UC Berkeley. And today I'm going to be talking to you about a new project that we're working on called PyWren, which is an effort to make it easy to scale data science across a large number of cores. This is joint work with Eric Jonas, who's a postdoc at the Rice Lab at Berkeley, Shifan Pu, who's a graduate student there, and Ben Recht and Jan Stoika, who are both faculty at Berkeley. Just some context as to who I am. I'm a PhD candidate. I used to be in the AMP lab at UC Berkeley, which is where the Spark project was developed. And I'm part of the Rice lab now. And my dissertation has been on doing system design for large-scale machine learning. I was a founding PMC member in the Apache Spark project, and I've contributed to various areas of Spark, including Spark Core, MLlib, and Spark-R. But today I'm going to be taking a different track and talking not about some of these contributions that I've done before, but about this new project that we're building in order to enable data science at scale. So when I talk about data science here, the motivation for this work comes from a specific kind of data science, which is on using large amounts of data in scientific applications, which has become the case across a large number of domains. So what are some of the examples of these scientific applications? So these are a few of these examples come from, for example, astronomy, where we collect telescope data from a large number of stars and planets and so on. One such example is, for example, data collected from the sun, which is, there's only one sun that we have, but we get around like 2 petabytes of data from it, from a NASA telescope that's like positioned on the sun. But there's also other areas, for example, mapping out the human brain or to record how every neuron in the brain behaves. And we have a lot of neurons in our brain, and so this generates a large amount of data. So for example, some of the recent studies generate around like 12 terabytes of data every second of scanning the brain for the neurons that exist out there. So what are some of the applications that are enabled by these large data sets? So in the case of the sun, for example, this is a real-size image of like how the Earth looks when compared to the sun. There are a large number of interesting aspects that we can study about the sun and how it impacts the Earth. So one such workload, for example, is studying how solar flares happen and seeing if we can predict when solar flares will happen ahead of time. So a recent project by some folks at Stanford and Berkeley have studied how we can do this by analyzing large amounts of telescopic data that we are collecting right now. Similarly, for the neuroscience data, where the goal is to map out the entire human brain, the human brain is an extremely complex organ with a really large number of like neurons that are a part of it. And an interesting challenge here is to see if we can come up with a map of the brain at various scales. So what I'm showing you on the left here is a very zoomed out version of the brain and showing the various connections, but we also want to go to various scales. So this is, for example, a 1000x zoomed in version of the first image, and we can even go down to the synapse level, which is another 1000x zoom in from the neuron level, that is the middle figure. So doing this is pretty challenging because this generates a lot of data, and we need systems that can process these large amounts of data. But these are just two examples. These kind of like really large data science applications come up in various other contexts, including things like adaptive optics to do, for example, super resolution, in various examples like MRI and tomography, and also in like phase contrast microscopy. So all of these are applications that are, for example, are actively are part of research in science today, but the amount of data that these scientists are processing is growing, and so there's this question of how are these scientists going to be able to handle the large amounts of data that they need to process. So the state of the art for implementing all of these scientific applications is to either use an off-the-shelf tool like MATLAB, or in the case of astronomers, to use a tool like IDL to do most of their data analysis. So the questions that we asked when we started off this project was, how do we get these physicists and electrical engineers who are using MATLAB to write most of these applications to stop doing that and pick up some of the more big data friendly frameworks that we have? Or similarly, how do we go and talk to the astronomers and tell them to use more friendly practices and to use things like cloud computing? So I tried to take on this task where I went to hold these weekly computational imaging lunches in Berkeley. And so I went there and I gave a talk on how to use cloud computing to an audience which consists of like a large number of like computational imaging like researchers in their lab. And as I was finishing the talk, I got this question from a member in the audience, Ren, who's a professor of computational imaging at Berkeley, and he asked me, why is there no cloud button? And I just looked at him strangely. I was like, what do you mean by why is there no cloud button? And what he had to say was that, why should I need to understand all of these things that you're telling me? Why can't I just press some button and my thing will run on the cloud? So I went back and I looked at my slides and I realized that what I was telling them was very natural for me because I've been working on this for the past 5 or 6 years, but that it was actually really hard if you were not somebody familiar with cloud computing. Because, for example, I told them, you need to launch some instances if you want to do data processing. And so then they asked me questions about what kind of instance should I launch, what is the base image that I should be using? And these are questions that are hard to answer without knowing what applications they're running. Then they also follow on with questions like, how many of these instances do I spin up? Should I use spot instances or should I not use spot instances? And it gets really complex beyond a certain point, and then they just give up instead of, and forget about using the cloud. And finally, they also have this question of, oh, I need to maintain all of these instances I launched, and this is a lot of overhead, and this is just too damn hard for me to do. So we went back to the lab, and we decided, OK, so what do we need to do if we want this like magic cloud button, and what are the requirements that we need to satisfy? And so we came up with a list of these requirements, and the main requirements that we had was, one was we should have very little overhead for setup. That is, once somebody goes onto a web form and registers for AWS, they should be ready to start using the cloud, and you shouldn't have too many intermediate steps where you think about instances, AMIs, and all of this stuff. Also, we wanted to be as low overhead as possible in terms of the programming framework, and that anybody who knew how to use Python should be able to actually use this framework, and they shouldn't need to walk through some very complex tutorial or to understand complex programming paradigms and things of that sort. And finally, we want to target a wide variety of jobs, but most of these scientific applications were our motivating use case, and thus we only want to target jobs that ran in the minutes or more regime. We weren't very interested in super low latency or for jobs that ran for multiple weeks or something like that. So out of these motivation steps came about this software project that we're building, which is called as PyWren. It's hosted at this website, PyWren.io. Just a little bit of background on the naming. The big bird that you see on top is a condor, which for those of you who know the cluster scheduling history, is this large project that came from Wisconsin to do cluster scheduling on a grand scale. Wrens, on the other hand, are really tiny birds, which are rather small, and PyWren, hence, is this really small project that is attempting to achieve the similar aspects as Condor was trying to do at a much larger scale. So how do we get started using PyWren? You literally can just type a pip install PyWren, and PyWren should be installed for you. It's a Python live package that's published on pip, and there are a couple of versions updates that we've done so far, and it should work with all the usual install mechanisms that you expect from a Python package. And how do you use PyWren once you've installed it? You can just import it like any other Python library. So for example, at the top of this notebook that I have here, I have import PyWren as a line on top. And the only setup line that you need to do is to get a PyWren executor running. So for this, we have this command called pywren.default executor that gives you this executor. Once you have the executor, you can run parallel programs by using this map function, which takes in a list of data points that you need to process and a closure or a function that you want to run on it. So in this case, add1 is this closure that we're executing, and xlist is this range of 10 numbers that we're passing in as an argument to map. So we wanted to model the API very closely to the Python Futures API because it's a well-published standard that a large number of Python users are familiar with. And so the return value from this map is a set of futures that has the same API as Python Futures. Given that we have that, we can then print the result from each of these futures by invoking this result function on individual futures. So when you hit that line f.result, that'll trigger a bunch of jobs to run on the cloud, and you will see a print line that looks like this as shown at the bottom of the screen. So this is the end-to-end user experience. It's literally pip install, import PyWren, and then a map function that you can run to do parallel computing, which we believe is a significant improvement over the amount of complexity that users need to think about today. So how does all of this work as sort of magic underneath the covers? A lot of this work exploits some of the recent trends of using serverless architecture in large-scale data centers. So I'll go into a little bit more detail in the rest of the talk of our design and implementation of this framework using serverless architecture, and I'll conclude with some of our thoughts on how we can improve performance and make and support more richer primitives to handle a large variety of applications. There are two main components that PyWren was built on top of. One was this Python distribution from folks at Continuum Analytics that's called Anaconda. And this is a very nice Python distribution because it has a lot of the packages that are very popular that ship as a part of it. And the second technology that we exploit in order to get all of this magic working is AWS Lambda, which is a service that's provided by Amazon in order to run microservices without actually launching any servers. So a little bit more of background on AWS Lambda. This is a friendly-looking GIF that shows what AWS Lambda is supposed to do. On the top there, you have this bucket of S3 bucket where data items are sort of pouring in. And Lambda are these like functions that get triggered whenever there's a new data item in the bucket, and they perform some small computation and write out output to some database or data store that you have. Now, there is certain limitations that AWS puts on the Lambda architecture, and this includes, for example, a 5-minute runtime limitation, and a memory limitation of 1.5 gigs, and a 512 MB limitation on disk space that you have available. Now, this might mean that you're looking at this and thinking this is like a very, very weak sort of like runtime that you get, but the advantage is that you can get a really large number of these runtimes going on in parallel. And this is not just supported by Amazon. There's been similar efforts by Google using the Cloud Functions project, and also by Azure in this effort called Azure Functions that have a similar kind of like programming model and architecture. So PyWren is this like data processing framework which is built on top of such platforms. And so what is the advantage of using a platform like Lambda? So like I mentioned before, you get this sort of scalability for free by just increasing the number of like these Lambdas that you can launch. So if you're, for example, concerned about the total number of like flops that you can get by running all of these Lambdas in parallel, we have done benchmarks that show that you can get around like 30, 40 teraflops at the same time just by launching around 2,000 or 3,000 Lambdas in parallel. Now, you might say that's not really surprising because you got like CPU cores and you have 3,000 CPU cores that you're running at the same time. But also in terms of the I/O bandwidth to read and write to S3, which is a shared like storage layer, we similarly find that we are able to get linear scalability for a long time, and thus overall we can get around like 70 or 80 gigabytes per second for both read and write when scaling up to like 3,000 workers. So these are both promising results that show that we can get a lot of I/O and a lot of CPU very cheaply by using these like Lambda-based technologies that are available at AWS, Google, and Microsoft right now. So I guess the natural question that you would ask is that, so what can I do with these Lambdas? And especially, I showed you this like simple map function that exists in PyWren. What can I do with this map function? So there are a number of workloads that just work by just using this map function. For example, ETL, where you have a large number of data objects and you want to perform some transformation on them before you load that into a database. This can be expressed as a really parallel map function that runs across all of these objects. Similarly, a number of machine learning applications involve a lot of like parameter tuning, and these parameter tuning tasks can be easily expressed as a giant map function that runs across the entire parameter space. So what's shown on the right here is a robust Kalman filtering example that ships with the CVXPy Python package, and we are able to parallelize every little square on that grid in order to run in parallel using PyWren. So just to show you a more specific example, we did this task where we took all of the 1.4 million images that are a part of ImageNet, the image classification benchmark, and we tried to do some pre-processing, which is similar to an ETL task you might do with other data sets, where we were computing this gist image descriptor, which was basically some random Python code that we got off the internet. It does compute the correct gist, just in case you're wondering. So here is an example of how the execution workflow looks when you run it with PyWren. And each of these individual dots represent one of these PyWren tasks that are executing. So on the x-axis here, you have the time taken. And on the y-axis here, you have one line for each of these like tasks that we're running. And we're running 3,000 of these tasks in parallel. So what we see from this graph is that it takes some time for us to launch all of these executors, but it's not that high. It's around like 20 seconds or so. And that once the tasks come up, they take some time for them to be set up. And I'll walk through what are these setup steps in the later part of the talk. But the setup time is typically pretty short. It's like 5 to 10 seconds. Then we perform the actual computation. This is computing just on these images in this particular example. And that takes around like 70 or 80 seconds for the execution to actually happen. And following that, we then ship the results back into S3 again, which are the computed gist descriptors. And writing out output to S3 also takes around 20 seconds or so. But one thing you might notice is that it's not an actually very uniform distribution. And you actually see a lot of like stragglers when you try to do this. You can actually see that a little bit more clearly using this histogram that I've plotted, where for each of these phases of computation that you have, there's a histogram showing how long it took. So we can see, for example, here that setup time, the median is around 18 or 19 seconds, while the time to fetch the result is around like 30 seconds or so in the median. But the good thing is that around 80% or so of the time is spent doing actual work, which is these red bars that you see on the right-hand side. So how does all of this actually work out in practice, and what are these steps involved in setup and compute and result fetch that I told you before? So the way the PyWren implementation works is that when you write this map function, and let's say you have a function and you have a particular data that you're running it on, this actually goes it first tries to serialize the function that you have and tries to dispatch the function and the data you're running on onto S3. So this is put onto S3 in some pre-specified buckets, and then we invoke Lambda to actually read the input and the function from this specified S3 bucket. So when we invoke Lambda, what that results in is that AWS spins up all of these Lambda cores to be executed at various parts of their data center. And once the Lambda cores come up, they pull the jobs and the data that they should operate on from S3. And this is the part of the setup process that goes on, is that they also set up this Anaconda runtime that's actually going to execute the function that we captured. So once the Anaconda runtime is set up, we then use Python just to execute the user-defined function that we are actually running. And while the user-defined function is running, we are constantly polling S3 for results that might have already been computed. So this is the step that your laptop is doing to figure out which of these tasks have completed and which data is now ready to be consumed as a result. Now, once the Python code actually finishes execution, we pickle the results from the output of the Python function, and then we stick the results into S3. And once the results are available, we are able to actually unpickle it and return it to the user. So it's a pretty simple execution flow, but it just shows that hidden away from the user and without launching any specific servers, we're actually able to support a pretty generic like execution framework out here. One of the key parts in supporting this execution framework is the serialization libraries that we use. And this is one of these scenarios where Python, being a dynamic and interpreted language, is of actually great help. And thus, we are actually able to serialize a really large number of functions effectively. We actually use the Cloud Pickle library, which PySpark also uses, and a number of contributions from PySpark have helped make it like a more robust serialization library. And we reuse all of those efforts in order to support serializing Python functions in PyWren. There are still some challenges in terms of how do we handle modules, and specifically how do we handle modules that have C libraries inside them. A lot of the interesting Python packages that you imagine, like NumPy, CVXPy, and SciPy, all of them use a number of C dependencies, and thus this approach of like serializing everything dynamically does not work out really well when you have C dependencies. So this is the reason why PyWren supports a number of like custom runtimes that you can build. And these runtimes, you can think of them as similar to like Docker images, where you pick a list of packages that you want to put in, and you can build a custom runtime that is already installed for you as a part of your Lambda execution. So the big challenge here is to make the runtime as small as we can in order to fit the Lambda restrictions. The image there is a Barbados thread snake, which is the smallest snake in the world. And it's meant to indicate the fact that we're trying to really compress all of these like big libraries like NumPy and SciPy into a very small 512 MB limitation that AWS Lambda has. So the way we do that is that we start off with a default Anaconda distribution with all of these packages installed. We run conda clean in order to reduce the packet size to, let's say, 977 MB. We then eliminate a number of like package-specific directories to get it to 946. Delete some more non-AVX2 MKL libraries, which actually has a significant win, gets us down to 670. There's a lot of shared libraries inside that. We strip all these shared libraries from debug symbols, get it down to 510, and then we delete all the PYC files that are present as well to get us down to 441 MB. So that basically gets us down from 512 to 441. So this is actually an automated script right now, so if you actually have your own packages that you're interested in, you can easily build a custom runtime. Some of the work in progress involves working around a number of the limitations that are present in AWS Lambda and in systems like S3, and also an effort to support richer operations. I'm only going to touch upon the richer operations in this talk. I'd be glad to talk about the other stuff after I'm done. And one of the main richer operations that we're looking at is what if map is just not enough? What if you want to do some other processing? Because, for example, let's say your data analytics pipeline looks something like this. You start with raw data, you do some ETL, you do some featureization, but you want to do some large-scale machine learning at the end of it. Now, obviously, this ETL and the featureization steps, like I mentioned before, are very good fits for PyWren, but large-scale machine learning is really not, and that makes Jeff Bezos unhappy because we can't use AWS Lambda. There is a radical idea, though, which is that what if we can actually do all that machine learning on one machine, because the data set actually reduces once you do all of that ETL and pre-processing. And this is something that actually AWS can support, and so probably Jeff Bezos is happier. And specifically, there are instances that can give you up to like 2 terabytes of RAM, which fits a large number of these featureized data sets, and they're not that much expensive. So PyWren supports this mode where you can run what we call as these single machine reduces, where you collect all of the data from the previous map function onto a single machine, and then you execute a Python function to execute the reduce. So this is in order to enable a large number of these machine learning workflows. Now, the next thing that we're considering is that let's say the single machine reduce is not good enough for you, but you actually want a full-blown shuffle similar to what you are used to with a system like Spark. And in order to test out how well these shuffles can be executed, we are playing around with the sort benchmark. Now, as some of you might remember, Spark was one of the systems that actually won the sort benchmark in like 2014. And so I think this is an interesting playground to test out the scalability and performance of a new system. So we implemented a TerraSort implementation using PyWren. And it's a two-stage implementation, like similar to the Spark implementation. The only difference being that we store the intermediate data in memory. So we actually use an elastic cache cluster with Redis installed in it, and that stores the intermediate data, and the output is again written back to S3 at the end of it. This is very recent work, so I'm just showing you some recent results that we have from running TerraSort. And the x-axis here shows the time taken, while the y-axis shows the number of like Lambda workers that we have and the number of shards in the elastic cache cluster that we have. So what we see here is that as we scale the number of Lambda workers and the Redis cluster size, we are actually able to improve the performance quite a bit. And for a 1 terabyte sort, it takes around 204 seconds or so. The other noticeable fact here is that there's a breakdown of time taken in various parts of the execution. And you can see that most of the execution time goes into S3 read-write or Redis read-write. So optimizing the storage systems and how we access the storage system layer is something that we think can actually improve the performance further. There's a number of other efforts that are in progress. Shifan Pu, who's a graduate student at Berkeley, is working on a new scheduling engine on top of PyWren. And this is to support features like doing rate limiting or to do straggler detection and mitigation, which, as we saw in the graph before, are problems that we run into when we have like thousands of cores. But these are just some of the initial steps, and we believe that there's a lot of interesting problems to be explored in this like serverless architecture mode that we're going to execute in. And thus, we are really interested in hearing about what are some of the other use cases. I talked about a number of like scientific use cases at the beginning of the talk, but we'd also be really happy to hear about enterprise use cases that you think fit this kind of like model of execution. And also we're working on circumventing the various limitations of systems like Lambda and S3, like I mentioned before. And finally, in terms of the primitives, we are happy to explore newer primitives, and we think this really depends on the use cases we plan to support, and thus it will be awesome if we could hear more about other applications that you think will better fit this model. So just to summarize, the PyWren project has a goal of making it very easy to scale data science, and especially to run these complex scientific applications at a very large scale and lower the overhead of doing that at the same time. All of our code is on GitHub. It's at github.com/PyWren/PyWren, and our website, PyWren.io, has some documentation on how to get started. And with that, I'll take any other questions. Thank you.
Hey, Shivram. So I have a question. So I've never used AWS Lambda, but you mentioned that other cloud providers have, similar services. Have you guys done any work towards, sort of integrating with them and comparing how this works out? And also, one of the problems I've had recently is there's the proliferation of different frameworks. Like now there's like Ray, there's like Flink, and Ray seems to have similar goals, even though their underlying philosophy is very different. So would, going into the future, would there be sort of, and they're also from the same place, right? So would you guys be working closer together? Yeah.
Yeah, thanks. That's a great question. I'll answer the two parts of the question separately. For the first part, so you do mention a good point about different backend providers and how specific it is to AWS versus Google or Microsoft. So one of the things that we are recently doing is having an architecture where you can plug in different backends for storage and for compute and so on. So you can plug in, for example, S3 as your storage backend or Google Cloud Store as your storage backend, and then run your compute based on data stored there. This Google one specifically, we actually have an implementation that we're testing out right now, and we hope to have it merged into the PyWren mainline pretty soon. Regarding a second question of the proliferation of compute platforms, I think that's a good point. I mean, I think the projects are trying to explore different target applications right now. PyWren is heavily motivated towards usability and making it much more easier to use and making it much more easier to scale these kind of embarrassingly parallel applications. While I would say that Ray is more focused on more complex ML applications. But things could get integrated in the future because, for example, the same PyWren API could be supported by an execution runtime that looks like Ray or that looks like Spark. And similarly, some of the work that we're doing in terms of the organizing storage and compute in the backend could become part of the backend for each of these engines. But I think as a research project, it's just easier for us all to explore different things at this point of time.
Hey Shriram, any reason not to go with Apache Spark itself? So so you have mentioned you want to have richer primitives, right?
Yeah.
So yeah, that's one question, and I have one more question. Mm-hmm. So in your Terasort slide, you have mentioned you use elastic cache, right? It reduces 30 workers, right? So even in the in that thing itself, you still use Lambda for reduce, right? Mm-hmm. Okay, cool.
So to answer your first question, yeah, it's a good point. I mean, I think Spark has a really rich set of primitives, and it is very powerful. And I think the way we're looking at it is that this is still a much more simpler framework than Spark right now. It doesn't really have all of the same capabilities that Spark has. But it's more focused on this serverless execution model where, and the question is what are the primitives that make sense to support given that you're working in the serverless environment? And we are hoping that the answer will be there's a smaller set of primitives that are sufficient or that are powerful in this particular setting. But it's a thing that we're exploring right now. So we don't know the answer to that question really well yet. And to the second one, yes. So the Lambda actually reads from the elastic cache and writes it out to S3. So they're both running in parallel, actually, both of the parts of the sort benchmark. Yeah.
Hi, yeah, thanks for the presentation. That was really good. It's interesting because last week we started looking into serving sklearn machine learning models through Lambda. Ran into a lot of space issues. Is that something that you're working on or have experience in?
Yeah, so I mean, I think we do have a runtime that has sklearn inside it. I think the tricky part there, if you're serving models especially, is to consider the size of the model itself. Because I think packaging sklearn as a part of the Python runtime, that's something actually we have code to do. And I can point you after the talk to specifically on where to look at. But I guess you also have this extra dimension, which is the model size. So compressing the model or performing other tricks on making the model smaller are probably very important to also consider with that use case.
All right, I think we have time for one more question here.
Thanks for the nice talk. I have one quick question, which is, can PyWren be used along with the AWS step functions?
What was the last part of the question? Along with Databricks? I didn't get the last
AWS step functions.
Oh, AWS step functions?
Yeah.
I'm not really familiar with what AWS step functions are. Can you describe that very?
Well, it takes a step above, beyond Lambda and can put things together, which kind of is automated.
I see. So it's sort of a workflow manager for
Yeah.
Lambda. We haven't tried it out yet. I mean,
All right.
so what PyWren does is it installs a custom Lambda handler. So there's a particular Lambda function that it installs. So it's probably possible to call that Lambda handler from AWS step as well. So it's probably possible, but we haven't looked at it so far. Yeah.
All right, let's give one more round of applause.
Thank you.